talk. He'll be talking to us about ARTEMIS. Big surprise. Lunar exospheric ions observed by LADEE and ARTEMIS. Thanks, Jasper.
So this is actually a science talk, and I'm not sure why I'm in this session, but since I'm in this session, I'll give you guys a quick status update on a few missions. As you heard, LRO is still going strong. ARTEMIS likewise is also doing very well. Both probes and all the instruments are healthy and still operating just fine. As you know, ARTEMIS is a mission which kind of straddles a couple different divisions. We work on the heliophysics and the planetary side of things. And in recent years, the focus has been a little bit on heliophysics because we've been collaborating with Van Allen probes and MMS now. But we still continue to work on the planetary side of the fence too, and you'll see that throughout the week, I think. So these two missions are still going strong. The third one, LADEE, of course, performed a cratering experiment and will not be resurrected anytime soon. But we still have a treasure trove of data that we're analyzing, and you'll see some of that in this talk and throughout the week. And those results will continue to come out because there's a lot there that we're still looking at. Okay, so that's it for mission status. The rest of this talk is science. So let's talk about the lunar exosphere, this tenuous non-collisional atmosphere that the moon has. How do we measure this exosphere? Well, there are a couple different ways you can do it. Of course, in this wonderful image taken from the Earth, you can actually take pictures of the atmosphere, and this works really well for something like sodium, shown here, that has nice strong emission lines. For other gases, it doesn't work so well. Another thing that you can do that LADEE also did to great effect is actually fly through this atmosphere and scoop some of it up and sample it. This also works well, but you need something that has a relatively decent amount of density that you can actually pick it up and measure it. But there's a third way, which is what I'm going to talk about today. It's a very Buddhist technique. Of course, there's plasma around the moon. That plasma is flowing. That plasma has a magnetic field. Through the wonders of electromagnetism, if you have a flowing plasma with a magnetic field, you get a motional electric field. So you have an acceleration source. This is good for measuring stuff. Now, if you can just find an ionization source, like, say, sunlight, what you can do is you can produce an ion from the exosphere. That ion will be accelerated along the electric field, and if you have an ion mass spectrometer in orbit, you can make very sensitive measurements of the exosphere. LADEE, of course, does not have an ion mass spectrometer. It has a neutral mass spectrometer, but the way that that instrument works is actually very useful. The way that it works, of course, is that there's a filament which boils off hot electrons. You electron impact ionized gas, and you actually mass analyze these neutral atoms as ions. Now, of course, if you just turn off this filament and you change a couple voltages around, you can also use this instrument to measure ions. And that's what I'm going to be showing you today. About 70 or 80 times during the LADEE mission, we performed ion scans with the neutral mass spectrometer. To do that, we turned off the filament, we changed a couple voltages to make sure that we were accepting ions and not neutrals, and we also reoriented the entire spacecraft. And we reoriented it in this way. We reoriented the spacecraft so that the NMS aperture is pointing south out of the ecliptic, rather than in the normal RAM direction that we would use to measure neutrals. And the reason we did that is that the prevailing electric field direction of the plasma tends to be either northward or southward for a nominal Parker spiral orientation. So we just picked northward, and we looked for times when the electric field was northward, and we just had to get lucky because we programmed these scripts in advance not knowing which way the electric field was going to go. But we got lucky a few times, and we saw this sort of case where the electric field was going north and accelerating newborn ions from the exosphere into the aperture of the NMS instrument. Now, of course, LADEE doesn't have anything that measures the electric field, and that's where ARTEMIS comes in. We have two ARTEMIS probes. One of these guys, sometimes may be in the wake and not measuring the plasma electric field that we want to know about, but at almost all times, at least one of the probes is upstream, serving as an upstream monitor, using measurements from the ESA instrument to get plasma velocity, and from the FGM instrument to get magnetic field. We can figure out the motional electric field of the solar wind, and we can determine whether or not we should be seeing newborn ions from the lunar exosphere in the NMS instrument. So here's an example of the data. These are two different ion mode scans. The top panel there shows the position in selenocentric solar ecliptic coordinates. Little bar there shows whether you're in sunlight or in shadow. And then there's a plot of the vector components of the electric field, and this very important angle. This angle is the angle between the electric field and the direction that would take ions into the bore site of the NMS instrument. So when that angle is close to 0, it tells you that the electric field is at least close to pointing into the instrument. When it's not close to 0, then it's pointing somewhere completely off in some different direction. You shouldn't be able to see pickup ions from the exosphere. So here's an example of the data, what the instrument actually measures down here. I should mention that we do not sample every single mass channel here, so there are stripes where we are sampling the masses, and there are some holes where we didn't actually sample those mass channels. But this is a typical activity where the field is well aligned, and you can see there's a smattering of counts throughout. Of course, there's a detector in here that has dark counts and so forth, so there's always a background. But there are some real clear signals that show up. There's some stuff down here around mass 2. There's a mass 12 peak. There's a 17 and 18 peak, but more on that to come. There's some stuff around here, 23, 24. There's 28, and up here there's 40, our friend argon. So this is all good news. The one on the right is a little bit more confusing because this is the time where the electric field is pointing the wrong way, and we're still seeing some stuff at 17 and 18. If we didn't have Artemis, we wouldn't know that this is background, but this is also background of a form. It's not the lunar atmosphere, it's the spacecraft's atmosphere. Somehow there's water getting boiled off of the spacecraft, forming a little coma, and that's getting into our instrument. So don't anybody get excited about water, at least not for this particular measurement. As you can see, these are low count rate kind of measurements, so you need a lot of these to build up some statistics. So what I'm going to show you now is basically co-adding these count rates over the whole mission. And as you can see, the sampling of masses is incomplete here. There's a stick here where we measured the mass, and there's none where we didn't. And these are average count rates seen throughout the mission. So you can see a number of interesting species on here. First of all, you can see some noble gases, and that's pleasant because we've also measured these in situ in neutral form. You can see some other things like H2, sodium, potassium, which have been seen with various remote spectroscopic techniques. And you can see OH and H2O, but again, this is pretty clearly a background, and don't get excited. And then there's some interesting things here. There's a carbon peak, there's a nitrogen peak, and there's this whopping big peak at mass 28, which is our biggest signal. Which unfortunately is a little bit ambiguous because there's 3 species that could be landing in that bin. There could be carbon monoxide, there could be silicon, or there could be molecular nitrogen. The preponderance of the evidence right now, I would say, is pointing towards it being mostly CO, but in principle it could be any of these 3 things. Okay, so now let's bring the electric field into this because we can tell which one of these are signal and which one of them are background. So now I'm going to separate the data into how well aligned the electric field is. And I'm going to define as signal these cases where the electric field is within at least 45 degrees of the aperture. Within uncertainties and fluctuations in the field, there's some chance that we're actually getting real ions into the instrument. And I'm going to define everything over here as background, where there's absolutely no way that the electric field is pointing the right way. And now the sticks up here correspond to that. The white is the signal, the blue is the background, and then the red is the background subtracted. In other words, the signal minus the background. And most of this stuff holds up. The noble gases still look good. There are nice red bars here. H2 and sodium and potassium still look good. And carbon, nitrogen, and this mass 28 peak hold up very, very well. You can see that the signal is orders of magnitude bigger than the background, especially for this mass 28 peak. So this is really a signal. It's really the lunar atmosphere. This guy, on the other hand, the background is bigger than the signal. We're not measuring lunar water ions, unfortunately. You can do more. You can rigorously define a detection criteria using standard statistics, take the amount of observation time, define a background, define what a 3 sigma criterion should be. Those are shown by the green sticks here. And then the signal, the background subtracted signal now that we actually measure is the red. So anywhere where you see red poking up above the green, it's at least a 3 sigma detection. All the ones that I've labeled on here are at least 5 sigma detections over the lifetime of the mission. So these are real detections. We're really seeing these species from the atmosphere, and they're really going in the right direction. They're really ions that are being born from the atmosphere, accelerated along the electric field, and we're happily seeing them. Okay, so we can do a little bit more than this. We can look at the local time dependence of these signals. We have enough of these measurements that we can bin things by local time. And here's what that looks like. Again, these are low count rates, so things are a little bit noisy, but you can see some interesting things on here. One thing that's nice is that you don't see much back in shadow, and you better not because there's no ionization source back there. There may be a little bit of charge exchange from plasma and so forth, but you really shouldn't see a lot of signal back here, and we don't. Spacecraft sunrise is round about here, and that's where you see everything come up. And you can see some other interesting wiggles on here. So these are the raw count rates, and you might think you're done, but you have to take into account the sensitivity of the instrument, and that turns out to be a little bit complicated because it's a very narrow angular aperture, and so things like the spacecraft velocity actually matter. So we ran a model to look at what the sensitivity to these different species should be, and I was really surprised when it came out like this. This is a case where I put a bunch of physics into my model, and then what came out the other end really surprised me, but it turns out to be right, and here's why. The electric field has no x component, so when you're flying around the terminator with a large x velocity, it's like driving into a rainstorm. If you drive too fast, all the water droplets hit your windshield, and they don't make it into your measurement aperture. That's particularly bad for heavy ions because they go slower for a given energy, and so the spacecraft velocity matters more, and so we have a big dip in sensitivity here around the terminator for the heavy ions. So you have to divide this out to get something like a production rate. And let's see what that looks like compared to some ground truth. So now these are measurements of neutral species from the same instrument, but a very different measurement technique. You can see the helium, neon, and argon for this single orbit. Let's see what our derived production rates look like on there. Now I'm going to scale the vertical axis arbitrarily just to make it fit on there and look nice, but what you see actually looks pretty pleasant because here's the approximate location of spacecraft sunrise. In other words, the point where we get into a region where there's a photoionization source. And here's the neutral distribution in red, and you can see we see all of our count rates when we get into the sun, and they have a local time dependence that looks plausibly similar to the neutral distribution. So we think we're measuring the same thing, which is a nice thing to think. This is argon. It works really well for helium and neon. Helium and neon are much more concentrated on the night side, so we don't actually get to see most of the distribution. But if you look at what we see, it looks pretty reasonable. The helium is pretty noisy, and that makes sense because the helium is very variable. Stay tuned for Dana Hurley's talk later in the week. The neon looks so perfect that it's probably an accident. It looks exactly like what you would expect if you convolve photoionization with this neutral distribution. So we're feeling pretty confident that we're measuring the right things. Now let's get to the stuff that we didn't so much expect. These carbon-bearing ions, mass 28 and mass 12. Mass 12 is unambiguous. Mass 28 we think is probably CO. And these are interesting too. Notice that they don't come up right at spacecraft sunrise, other than this little blip here. Don't worry about that little guy. But they don't really start to come up until around 270, 280 longitude. And so that may be a sign that these are things that are desorbing off the surface that are a little bit sticky. You have to get the surface hot enough before they start to boil off of the surface. That's just a supposition, but it might be borne out. So how do you get these kind of carbon-bearing ions? Well, it's actually not too hard to get them to the moon because there's carbon in the solar wind in the form of often highly charged carbon ions, and there's also carbon in micrometeorites. So you've got at least two possible ways of getting this stuff to the moon. Once it sticks to the surface, you can get some of it off the surface in the form of perhaps molecular CO or CO2, and then again you've got a photoionization source. But you don't just get CO plus and CO2 plus if you hit these guys with photons. There's all different kinds of things that these molecules can split into, charged and neutral form. So there's all kinds of branching ratios here, and there should be a consistency check to this. Lo and behold, we actually see C plus and CO plus in about the ratio that these photoionization rates would suggest, or photodissociation rates really in the case of C plus. And what we find is that if we have about 10,000 per cc of neutral CO near the surface, that we can explain both the C plus and the CO plus that we see. So that's a fair amount of neutral gas near the surface. 2 minutes. Real quick, how does this compare to previous measurements? Not too badly. Here's some measurements far from the moon by wind. You can see they had a big peak at O+. Please don't ask me about O+, I have no idea. But they also saw some stuff at C+, and they saw a big peak at 28. They were interpreting these as ions directly from the surface, so they called that peak silicone. But given our geometry, we know we're looking at stuff in the atmosphere, and I think it's more likely CO+. Kaguya also measured ions, and they see some similar things to what we see: helium, carbon, oxygen, sodium, and they have a big peak here that they're calling potassium. I've talked to Saito-san recently, and he is willing to admit that that peak is probably argon. So we're in pretty good agreement with what's come before, except for this big CO plus peak is still surprising and maybe a little bit different than what others have seen. Maybe consistent with what wind has seen. How about Artemis? Well, with Artemis, we also measure the pickup ions. Here's a distribution of the pickup ions, and in this particular observation, we got really brave, and we tried to fit it to a 5-species model. And knowing what we knew back then, which was not very much, we called those species carbon, oxygen, sodium, aluminum, and argon. Now, knowing what we know today, I think I would relabel these two bins neon and CO. I had no idea that there should be neon at the moon, but lo and behold, there's lots of it. So if you rerun this model and you relabel these species, you come out with a table something like this for surface densities, and it's pretty reasonable. The neon and the argon match what we know. The CO is within limits. The O is a puzzle, and the C is a puzzle, because both of these guys are a little out of bed with known spectroscopic limits. But what we didn't know then was that C could come directly from CO. In other words, you don't need a bunch of neutral carbon, you just need carbon monoxide and sunlight, and you can get some C+ out of that, and it's in the right ratios. And in fact, it explains a puzzle that we had here, which was that the scale height that we came out with for the carbon was too low for a light ion. But of course, if that's a direct product from the CO, then it should actually have the scale height of a heavy ion, and it all makes sense. So there may be a nice consistency check here. I'm about out of time, but just a word of what we want to do in the future. We want to go back to the Artemis data with a fine-tooth comb now that we think we know what we're seeing from NMS. And we'd also like to look at some data from the other instruments on LADEE, which are also sensitive to ions. So I will leave you with the nuggetized version and take any questions if there's any time.
Great. We have time for questions. Please state your name.
Paul Hain, JPL. Thanks, Jasper. I'm really glad that people like you exist who are able to look at these multiple different data sets from both LADEE and ARTEMIS and all the other spacecraft. But I mean, the carbon thing is really interesting, and I was wondering if you guys have thought about the flux of CO2 to the cold traps. There's plenty of places on the moon that are perennially below 60 Kelvin or so, and those would be good cold traps for carbon dioxide.
I've only thought about that because I've seen what you and Dave Page have presented along those lines, but it'd be really cool if that worked out.
Also, have you compared the different, how eccentric is LADEE? How much of a difference between the apogee and perigee of the orbit? Do you see much, I mean, is it vary or is it pretty round?
Over the course of the mission, we scanned a fairly wide range of altitudes, actually, and I've tried very hard to make a story about scale heights, and there's just not quite enough counts to really make that story, unfortunately.
Okay.
Okay, one more question.
Justin Simon, Johnson Space Center. So I was also interested in your CO story, and I was wondering if you had considered, you seem like you have internal consistency, but have you considered the possibility that the CO is being produced locally from the oxygen that you know is from the background? So basically, you took out the background that you counted, but you didn't take out the oxygen in the CO.
So
you could have.
Oxygen is a real puzzle because a number of spacecraft now have measured oxygen at higher rates than expected. We're still a little unsure as to whether we measured oxygen or not on LADEE. There were some issues with the data reduction scripts and so forth. So there may be oxygen data still hidden in those, but if there is, we haven't analyzed it yet.
It'll be pretty simple to just take what you had in the oxygen blank and then see if you can add that to the carbon to get the CO2.
Okay, I'd have to think about that a little bit. Thanks.
Yep.
Okay, go ahead. I feel bad.
Thanks. Big picture question regarding what we thought of where the exospheric comes from in the first place. Would you say that it's still consistent with the idea of sputtering things off the surface, or is it more looking like it's being brought in by meteors and whatnot, the exosphere?
Well, it's probably all of the above, right? Because you have to have an initial delivery mechanism to get the stuff there, and then you have processes that liberate it from the surface. Some of it goes back and sticks on the surface and has to be reliberated. So I think it's probably all of the above. I think if it's CO, then the way you get it off the surface is maybe more likely just thermal desorption, but there's always going to be a component of sputtering and micrometeorite bombardment besides.
Okay, wonderful. Thank you very much. Appreciate that. But before you leave,